Hello everyone and welcome to this last chapter of the graph course, Theory, Application, Algorithm and Implementation. So in this last chapter we'll be covering flows, network flows precisely. So we'll start by defining what do we mean by a network flow. We give some definitions and how we can calculate the flow, and then we'll move to a more interesting part, which is about the minimal cuts and minimum cuts, and we'll be linking those two information, so how we can calculate the flow, the maximum flow, and what's the relation with the minimum cuts and minimum flow. So we reach the third part, which is about the maximum flow, minimum cut, and we'll be covering the Fulkerson method, and we'll be implementing the Edmonds Karp algorithm as well. So we'll be reviewing some of the previous algorithm, so namely Kuhn's algorithm, because it will talk about the augmenting passes and stuff. So we'll start by the first part, which is about the network flow. So we already know what does it mean in network. So we have vertices, we have edges, and we have weights that assign to those edges. So a two-terminal network, so it's a network, and it has two special terminals. So we already talked about the source and the sink. So we already talked about that. So a source, so it's the vertex, so usually we call it as, so it has an in degree 0, so it means that as it just have an outgoing vertices, and the sink we usually call it t, so it has the out degree equal to 0, so it has some in degree, so it has incoming vertices edges but not outgoing edges. So all the remaining vertices, we call them intermediate. So those two, we call them terminals. So it's a network which has two special terminals, which are the source and the sink, and all others are intermediate vertices. So in general, we say that a network need not have any terminals, so there's no need to have S and T, and some may have several also, so we'll see how we'll deal with those conditions. But in our case, we'll focus on the two terminal problem with one source and one sink. So for each arc, we will associate a weight. We call it capacity C of the edges, that we call its capacity. So this is the usual definition of a network. So we have here an example of a network flow. So for example, if this is a transport problem, so vertices A, B, C, and D will represent points of intersection. It means so for example, if it's transport of merchandise, so it's like shipping should be transferred from an endpoint to another endpoint, as if you may think that those items as being transferred from a truck to a railway or ship or anything else. So just any definition of vertices that you can came up in your mind. For example, in a telecommunication context, you may think of the vertices as points where, for example, information is transferred from, for example, a local network to a WAN or MAN or anything else. So it's just a network, and we have some weight capacities that may define or explain any part of the concept. So what does it mean a flow, or what do we mean by a legal flow? So a legal flow, we usually call it a small f in a network. So we assign non-negative numbers, so it's called f of e. So for each edge, I'm assigning a flow, a non-negative number for each arc, such that we have the following conditions are true. So for each arc, for each edge, the flow is greater than 0 and is less than the capacity. So for example, if I have an arc and I can maximum send 7, so obviously I can send either 0, 1, 2, 3, 4, 5, 6, and 7. So for example, we can have here equality, so the maximum is 7 and I can send nothing. So this is the first condition. So this condition, it guarantees that the capacity of a given arc is not exceeded. The conservation of flow, so for each vertex V other than the source and the sink, we have that the sum of the flow from U to V, so U is any vertex in N in the network, minus the sum of the vertex of Vx is equal to 0. So for any vertex V, as if the network could be subdivided into two parts. So this is V, this is the part before V, so those are U, and those are X. So the flow here, the sum of the flow minus the sum of the flow here is equal to 0. So the second condition, it tells us that the flow is conserved. So if, for example, if I receive to my bank $10 and then I need to get $10, so it is conserved. So nothing is lost, nothing is lost or theft. So the second condition, which is called the conservation of flow, ensures that the flow into the intermediate vertex equals the flow out of it. So you may think of it as a flow of water passing through pipes from S to T. So in the first one here, the first condition, it says that no more water will pass through a given pipe that a pipe can bear. So obviously I cannot overpass some water from it. So it's not the Lebanese way. And the second condition said that there are no leaks at the joint pipes at the vertices. So it's very important to guarantee all these. So the general problem of interest in network problems is obviously to maximize the flow. I need to send the maximum number of flow, or the maximum number that I can pass into the network from the source, obviously, to the thing. Obviously, we should have always legal flows along the arcs of the network. So the total flow in the network, so it is equal to the flow that is out of the source, or it's equal to the flow that goes into the thing. So this is the source and this is the sink. So the flows goes from the sink and it flows into the sink. So this is the sink and this is the source. So it flows out from the source and it flows into the thing. So it's equal. The flow that comes out from us should be equal to the flow that comes into the sink. And obviously we need to maximize F. So for example, if I have, for example, this small network, just give you an example. This is S, this is A, this is B, and this is the sink. So for example, I have here 2, 3, 2 and 1. So you can say, for example, I can send here just 2. So I can send 2 here, 2 over 2, 2 over 3. So I can reach just 2. However, this is not the maximum flow that I can send. I can send also 1 along this path. So I can send 1 here and 1 over 1. And in T, I can reach, in the sink, I can reach a flow of 3. So the flow that goes out of S is equal to the flow that comes into the sink. So and we need to find ways to calculate this flow and to maximize this flow. So as you can see, this is the capacity and this is the flow. So we call slack, you already know that this is the difference between the capacity and the flow. So slack of E for every edge, it's equal to the capacity. So it's the maximum number that I can send minus the actual number that I have sent. So the slack, it represents the remaining capacity available in an arc. So if the slack of an edge is equal to 0, we call it a saturated. So there's no more, I can send any more flow from on this arc. So clearly, if every arc into the sink is saturated, then we have achieved a maximum flow. So if at the sink here, all the arcs are saturated, it means that I cannot send or receive more in this flow. So it's already saturated. So this is the maximum flow. I cannot receive more. This is the maximum that I can receive. Similarly, if from the source I have all the arcs saturated, so I have sent all what I can do. So obviously this is the maximum flow. We will see that neither of those situations is necessary, as we will see in this example. So we have here an example. So I will not give you the algorithm from the beginning. So we'll try to find a way to calculate the maximum flow, or to attempt. So there's an attempt, because we will see we will fail to achieve a maximum flow. So at first, we will start by assigning 0 flow to each arc. So as if there's nothing, I have sent nothing from source to the thing. So we will label them C of E, F of E. In some other books or in the practice, you will see them introverted. So for example, sometimes you write F of E, C of E. You should know that it's very obvious that F of E, the value of the flow, is always less or equal to the value of the capacity. So at first, I have sent nothing. So I have zeros everywhere. So it's already in the animation. So, and then we need to try. So we'll start by, I don't know if there's animation here. Okay. So we'll start by successively finding passes from S to T. So I need to find a path. directed path obviously, which we can increase the flow. So for each pass we will be able to increase the flow by the minimum of the slack value for arcs of this pass. So we'll try to find a path. So the first one is SCBT. So in SCBT, so I have here 5, I can pass 4, I have 7 and no, so here we have 3. So obviously if I want to pass a flow, the maximum flow that I can pass along this path is equal to 4. So the 4 is here, 3 is for this one. So let me go back. Okay, so we have 5, 4, and 7. So obviously I can pass 4. So what I will do is that I will try to pass 4. So I will decrease 4 along this path. So 5, I have passed 4, I have passed 4, and I have passed 4. So for now, the maximum flow is equal to 4. So the next question is that, can I pass more flows? Yes, I need to find just another pass. So for example, I can pick SCDT. So in SCDT, here I can still pass 1. Here I can pass 2, and here 6. So obviously I can pass the minimum slack, so it's equal to 1. So 1, it means here I have passed 5, and here 1, and here 1. So the total flow for now is equal to 5. I need to check if I can find another pass. So obviously there's this pass, and maybe this pass also, so there's a lot. So let's try SABT. In SAB, we have picked SADT. So we have here a slack of 9, we have here 3, and we have here 5. So obviously I can pass 3 along this path. So I will write 3, here we have 3, and here we have now 4. So for now we have 3 and 1 and 4. So we have 4 plus 1 plus 3 for now. So is there any more passes? So let's see. Yes, we have SABT also. So in SABT, so those are saturated arcs, obviously, because the difference between the capacity and the flow is equal to 0. So I cannot pass any more flows along this arc. So I need to find other passes. So we have this. So here the slack is equal to 6. Here we have 5. And here we have 3. So obviously I can pass 3. So I have here 6, 3, and 7. And okay, so I have passed 3 also. So for now I have my flow is equal to 11. So we need to check, is there any more passes that we can take in order to increase the flow. So as we can see, so we have these 2 arcs which are saturated, so I can do nothing more. So this arc is saturated, so I can work on this arc. So this one is saturated, I have 5, 3, so I can pass 2. However, from this vertex I need to use this one, but it's already saturated. So at the first look, this is the maximum flow. However, this is not the correct answer. So the total flow is 11. However, this is not the correct answer. So 11 is wrong. So the correct answer is equal to 12. So the problem here, so how we can increase the flow. So as you can see, we have here an example. So for example, we already knew that I can increase the flow on this edge, on this edge 2, on this edge 2, on this edge 2. However, on this edge, it's already saturated and it's equal to 4. So as you can see, if I want to increase the edges or the flow on these edges, we will use what we call a semi-pass. What does it mean, a semi-pass? So it's not a pass, it's a pass, but I will be moving in the opposite direction. So what does it mean, passing into opposite direction? So the difference is that if we travel the arc in the wrong direction, we will decrease the flow on that arc. So as if I'm getting, I'm getting back what I have done, what I have gave you before. Yeah? So I'm getting back what I have gave you before. So how much additional flow can we move along a semi-pass? So we can move the minimum of the slack value for the forward arc and the value and the flow values for the reverse arc. So if I have picked this semi-pass, so a semi-pass, I repeat, so it contains one edge in the opposite direction, and I can move the slack value, the minimum slack value on the forward arcs and the flow values of the reverse arc. So the slack value here is 3, 2, this is already saturated, so it's equal to 0, and this is equal to 1, and this 2. So I can move 1 along this. So let me erase all these and see what we will do. So as you can see here, I will remove 1, so it means that I will not send 4, I will just send 3. However, so now I have gained 1 here. However, I will send it into other directions. So what I will do that is I will send 7 here, plus 1 here, plus 1 here, and plus 1 here. So I will revert all these in order to do that. So after doing that, so now we can consider SAB CDT, so the minimum slack on the forward arcs, as we have seen, is equal to 1, and the flow on the reverse arc BC is equal to 4. So we can augment the flow by 1, as I have said, in the forward arc, and decrease the flow by 1 in the reverse arc. So we have found the minimum slack, so I will repeat. So we have here a semi-pass with one of the arcs in the opposite direction. So we calculate the minimum slack, so it's equal to 1. And we increase the flow on the forward arcs, and we decrease the, sorry, it's equal 3 here on the reverse arc. So what's the effect of that? It's that we divert 1 unit of flow from arc CB, so as if we have removed this one from here, and we have sent it through CD instead. So we have sent it here. Instead of going like this, I have sent it here. So as you can see here, we have augmented here 1. So at total, we have the flow equal to 12. And this is the idea on how we achieve maximum flow. So obviously, we will not be doing that. We will not be looking for semi-passes along the network, because this is not how we will solve that using a computer program. So we will be covering more algorithms, so namely the Edmonds Karp's algorithm, that will help us to find the maximum flow more easily than this. But this is the theory, and it's based, so even if when Edmonds Karp elaborated the algorithm, they have used the notion of semi-passes. So this was for the network flow. So we will be moving now to the second part, which is about the minimal cuts and minimum cuts. So we have already talked about cut vertices, bridges, and stuff. So we will see later at the end of the course that the Edmonds Karp's algorithms at the maximum flow can be used to prove Menger's theorems that we have already covered whenever we have talked about cuts and bridges. So in order to achieve a maximum flow in a network, so we will be using an important and powerful theorem due obviously to Ford and Fulkerson, which is called the maximum flow minimum cut, that we will cover in the last part of this chapter. So it will use the concept of minimum cut. So for a network N, if we have a source and a sink T of arcs, such that obviously every directed passes from S to T passes through at least one of the arcs of S. So a cut, it will cut the network into two parts. So I have here S, I have here T, I have here the intermediate vertices. So for example, this is a cut. So a cut, it will subdivide the arcs into two parts. The one that goes out from S and the other that comes into S. So in other words, so if the arcs of S were removed from N, so there would be no directed passes from S to T. So S is a set which we call the cut. Cut, it contains the set of arcs from S to T, and we will see later that the minimum cut would be equal to the maximum flow. So the value of the cut, or the cut value, is the sum of the capacities of the arc in the cut. So if I have decided that this is a cut, so we'll see later how we can choose a cut. So the cut, it will be equal, the value of the cut is equal to the sum of the edges, the capacities of the arcs in the network. So a minimum cut for a network is a cut that has the smallest possible cut value. The minimal cut, it means that if one of the edges of the set S is removed, the remaining set is no longer a minimum cut. So in other way, there is no redundant arcs in a minimal cut. We will see it in a while. So it should be clear that a minimum cut, obviously is necessarily minimal. However, a minimal cut is not necessarily a minimum cut. So I already covered that before. So we will take an example just to understand what does it mean a minimal and minimum cut. So at first we need to find all minimum cuts for the following network. So which of these cuts are also a minimal cuts? So obviously we must find minimal cuts set of arcs whose removal will cut off any possibility of flow from S to T. So if I, for example, if I say that this is just the cut, it means it contains just this arc. Obviously, I can still send some flow from S to T. So this is not a minimum cut. So there's a lot of possibilities. So SA, for example, if I do this cut, it means I'm cutting the network. So if I remove those arcs, obviously I can send no more flow from S to T. So the value of this cut is equal to 14. Why? Because it's equal to the value of the capacity. So 9 plus 5 is equal to 14. I can have also this cut. So obviously this is a cut because it will subdivide the network into two parts. So and if I remove those arcs, there's no way to receive flow into T. And the value of this cut value is equal to 13. So as you can see, there are different values of the cuts, and we can have many other cuts. For example, I can have this, I can have like this. So you can have a lot of types of cuts. So I have listed here all the possibilities. So you need to check for each cut that S and T should not be reachable. And I have here the value of each cut. So as you can see at the end, the last one, AD, CD, and BT. So I will erase all these. So if I remove AD, this AD, CD, and BT, so this, obviously I can send no more the flow to T. So in order to check that, so if I remove this, obviously even if I send flow to B, there's no way to reach T. We have here, we need to be sure that we cannot send flow along this edge. So we have removed this and we have removed this. So obviously there's no way, there's no flow that comes into D. So obviously S and T, they are into two separate parts, and the value of the cut is equal to 12. So this is very nice. We are in love with that. Why? Because as we have seen, this cut, the value of this cut is equal to the maximum flow, because we have already seen how we have calculated the maximum flow using semi-passes. So we will move here to the maximum flow minimum cut theorem. So any cut S partitions the vertex set into two sets X and Y. So as we have seen, we have two parts. We have this part and this part. So the set X consists of all the vertices that S can reach, and the set Y consists of all other vertices, obviously. So thus arcs of S is incident with a vertex in X and a vertex in Y. So we will say that C of S will denote the cut value of the set. So we have a theorem here. So if the total flow of the network N and S is any cut, so we know that the flow is less than or equal to the cut value. We have a corollary that says the maximum flow is less than or equal to the minimum cut value. We have, so obviously we'll not be showing all of these theorem. However, the theorem that we'll be using is that, and it's due to Fulkerson, is that for a network the value of the maximum flow is equal to the cut value of the minimum cut. So the cut value of the minimum cut is equal to the maximum flow. So as you can see, so I will go back to this because all of these are minimal cut. However, only this is the minimum cut. So the only minimum cut is AD, CD, BT, which has cut value equal 12. So it's the same value as the total flow we have found. So we have finished the second part, which is the minimal cuts, So we're moving to the maximum flow, minimum cut algorithms, namely Fulkerson method and Edmonds Karp algorithm. So in order to calculate the maximum flow, we will be talking about or introducing what we call the residual graph. So we have talked about it indirectly. So whenever we have talked about a slack, so given a flow F in a graph, so the residual graph, so we call it G of F. So it's directed graph with all edges of E they have. So all edges are strictly positive slack. So slack C of E minus F of E. So each one is labeled by its slack. So we'll see that, and it's very easy to do. So we may have back edges, obviously. So this may include back edges of the original graph. So if UV, if I have an edge that is not in the graph, so the capacity of UV, it will be equal to 0. However, the flow, I can send a flow because we have seen in semi-passes, I can pass a flow in opposite direction. So the flow of FUV is equal minus the flow of FVU. So this is very important. So if there's no arc in the graph, obviously its capacity equal to 0. I cannot send because this is the capacity. There is no arc, so there's no pipes. However, I can, if I'm considering semi-passes, the flow would be equal to the negation of the opposite direction. So we'll see that, how we will do that. So we'll be decrementing whenever we are going backward in the graph. So the fourth Fulkerson algorithm, so it's a simple iterative algorithm. So we will send a flow through pass P whenever there's an augmenting pass from S to T. So we'll remember that the augmenting pass, it was already part of one of the chapters before. So what does it mean, an augmenting pass P? So it's a pass from the source to T that passes through positive weighted edges in the residual graph. So in our case, an augmenting pass, so it's a pass that passes through positive weighted edges in the residual graph. So residual graph, I will repeat. So this is a graph. It will be labeled by the edges that they have strictly positive integers, which are the slack, and we may have some negative. It depends if there's an arc in the original graph or not. So we'll start by giving the algorithm and see how we can work on the residual graph. So first, I need to create the directed residual graph. This is very easy. We'll see it in a while. We set the maximum flow, so this is just a variable. So the maximum flow for the beginning is equal to 0. We look for augmenting passes from S to T. So if there's an augmenting pass from S to T, I will find F, which means the minimum weight along the path. So this is the slack, the minimum slack that I can find. I will decrease, so I will do minus on the forward edges on this path, and I will increase the weight of backward edges along path, and obviously I will increment the value of the maximum flow. Whenever there is no more augmenting passes, I will display the flow. So let us first just talk about the residual graph. Even if we will be doing the algorithm will be run more easily, even if let's say that we want to just find the residual graph of this network. So this network, it contains the capacities and the flows, and we need to find how we can calculate the residual graph. So as a reminder, the residual graph, it has a slack value on the arc, so it's equal to the capacity minus the forward edges. So from S to A, we know that it's equal to 10, so it's equal to 20 minus 10. On the back edges, so as you can see, there's no A to S, so it's equal minus of the flow, so it's equal to 10, so it's 10 equals 0, because the capacity, there's no arc from A to S, so the capacity is equal to 0. So I will go back to some of the slides. So the capacity is equal to 0, and I'm doing the slack, so it's C minus F. So I'm passing here minus 10. So 0 minus minus 10 is equal to 10. So A to B, so the slack is equal to 5. In the backwards, so I'm doing, so it's equal to 0. 0 minus 0 is equal to 0. So, okay, I can place 0. However, we can omit it because it's equal to 0, because I'm not passing any flow in the opposite direction. So we'll continue like this. I will not be doing all this because it will be calculated automatically whenever we are running the algorithm. So this is the residual graph of this network. So I will repeat. As you can see, there are edges on both ways, and all the arcs values are positive. The black ones are the flow that can pass, and the red ones are the flows that already have been passed. So this is the idea of the residual graph. Obviously, we will not be doing a residual graph from the middle of the network. We'll be starting from the beginning. So this is our running example. So this is our graph, and we need to find the maximum flow from S to T. So for that, we will start, so flow, it will start from 0, and obviously all the flows is equal to 0. So as you can see, at first, the residual graph is equal to the graph, because in the opposite direction, so this is, there's no capacities and there's no flow, so 0 minus 0 is equal to 0. So at the beginning, so each edge has the same weight as the original graph. So there is no need to create a structure for residual graph, because it's already the graph. So I'm working directly on the graph, and it's the residual graph. So the algorithm says that I need to find an augmenting path. So we already covered that, how to find an augmenting path, so we'll be implementing that later in a while. So an augmenting path, so I have found SCT. So what I will do so I have the variable flow, so I will find the minimum value of the value here. So this is the slack, because this is the residual graph. So the minimum between 70 and 25 is equal to 25. So the flow is equal to 25. I will decrease the values on this way. So 70 minus 25, and here 25 minus 25. And on the way back, I will put the value of the minimum value here. So on the way back, I will put 25 and 25. So this is my graph, and then I need to find another augmenting path. So here I have found SCBT. So, and the minimum value on the outgoing edges is equal to 5. So I will increase the flow by 5. So I have 25 plus 5. Now it's equal to 30. So I will decrease by 5 the path that goes from S to T on this way, and I will increase the path in the backward direction from T to S. So this is my newly residual graph. So it's here. Can I find an augmenting path? Yes, there's SBT. SBT minimum is equal to 30. So I will add 30 to my 30 that I found earlier. So now my flow is equal to 60. Again, I will decrease the path, the ongoing path, and I will increase the backward direction. So here I have the residual graph. So there's no more augmenting passes. So if I will look well, I'm going from S, so 0 here. So there's no way that I can take any more here. So I have 40. So if I go for 40 from here, so there's 0 here, 0 here. So there's no more augmenting passes. So I have finished, and this is the maximum flow, which is equal to 60. So we have found the maximum flow. So this is the maximum flow. And we know that if I found the maximum flow, and according to Fulkerson algorithm or theorem, the maximum flow is equal to the minimum flow. So, how can we find the cut set in this case? So the minimum cut value is equal to 60. So I just need to look for the zeros in my the values of the flow of the arcs. So I will pick this one, I will pick this one, and I will pick this one. So it's very easy to do. So this is my cut. So this is my cut. It will passes by zeros on the forward arcs, and automatically, because this is what I have sent along these edges, it will be equal, the summation would be equal to the maximum flow. So in other way to say that those arcs are saturated because the slack is equal to 0. So how can we, so the question here is, how can we find an augmenting path? Do we use BFS or do we use DFS? So the problem, so this is here the problem. So there are several ways to find an augmenting path, so or via DFS or via BFS. So for Fulkerson, they used DFS, and it was problematic. Why? Because let's take this example. I have this network from S to T, and at each time I'm using DFS to find an augmenting path. So DFS, if I'm doing just DFS, let's forget about the maximum flow. The path is equal S A B T, because if I'm doing that, this is the how we can do the DFS. So if he's doing DFS, so this is the first augmenting path, and then this is the second augmenting path. So at each time the residual graph will be decreased just along one way, and as you can see the arcs will be inverted. So at each time I'll be doing that. At the end, after 198 iteration, I will reach to the fact that the maximum flow here is equal to 200, but this is too much time. So if I'm doing a BFS, obviously it will be more easier and more convenient because I will be doing level by level, and it will be done that. So I will keep that for you. So just redo this example using BFS, and obviously you will not be doing 198 iteration. So for Fulkerson original algorithm handled network with integer or even rational capacities without any problems. However, they show that if the capacities were irrational, then their algorithm might be take an infinite number of steps because of this. So because they are using the FS. So Edmonds and Karp algorithm, they have fixed the shortcoming of this by using BFS. So this is why we have covered BFS. So it can be proved that after V multiple E BFS iteration, so this is the vertices and edges, all augmenting passes will be already exhausted. So before moving to the implementation of augmenting passes and algorithms, so let's do together some of the exercises in order to more grasp the idea. So we need to use the Fulkerson algorithm to obtain the maximum flow from S to T. So it's either for Fulkerson or you can apply Edmonds Karp. So it's the same because at the end we'll be using, in terms of solving, we will not be distinguishing between the FS or BFS, but in terms of implementation, obviously we'll be implementing for Fulkerson. So we need to find an augmenting path. So let's say I have SACT. So the maximum flow I can send here is equal to 2. So flow for now is equal to 2. So as you can see, the residual graph is equal to the graph itself. So I have sent 2. In other way, I need to place 0 here, 2 here. Now I have 2 here, 2, 2, and 1. So I have sent 2. This is what it remains, and this is what I have got back. Another augmenting path, I have SPDT. So here the flow is equal to 1 because this is the minimum. So I have here 0, 2, 1, and on my way back I have 1. Then I have let's say SADT. So SADT. So I have 1, 2, 2. So obviously the flow is equal to 1. So 1, I have here 0 because I have exhausted it. So it's equal to 3. Now I have 1 here. So on the go back, I have 1. And here I have send 3 because I have used it. And going back is equal to 0 if I'm not mistaken. 2. So I have 2, so I have 1 here and 2, so it's the opposite. So it's equal to 1, and here I have 2. Do I have more augmenting passes? So I have, for example, here SB, let's see, C, C. So I cannot see CT because it's already 0. I can go CA. So SB. So here SB. So there's 1. BC1. C2 1. 1 SBAD. I can go ADT. Yes. And the flow is equal to 1. So SBCADT. SBCADT. The flow is equal to 1. So if I'm doing that, so I have send 1, I will decrease it, SB. So now I have 2 here. Here I have send, I have 2, so I have send 1, and then it's 1 here. Here I have 2, so I have send 3. So I have 1, I will decrease on the ongoing and increment on the going back. So I will decrease here, 2, decrease 3. So I have here saturation, so everything is saturated, so this is the maximum flow, and it will be equal to 5. So I have the solution here, so don't worry. So we can check it, and we have all the steps. So another example, so use Fulkerson algorithm to obtain a maximum flow from S to T. So you can pause me if you want, try to solve it by your own, and then try to find the augmenting path. So we have SABT. So the maximum here I can send is equal to, the flow is equal to 2. So I will decrement on the going and add on the going back. So decrement 2, it means 1, 4, 0, 2, 2, 2. I have SADT, so SADT, and the flow here I have 1, 1, 6, so the flow is equal to 1. So I will decrement on going and increment and going back, 0, 1, 5, 1. We have also SCDT, 4, 1, 5, so the flow is equal to 1, 3, 0, 4, 2. So we have the remaining ones that are on the here. So SE, I have SET, SEDT. So let's do SEDT, 5, 2, 4. So the flow is equal to 2. So I have sent 3, 2, 0, 2, 2, 4. And at the end I have SET, so the flow is equal to 1. So we have here minus 1 is equal to 2, 3, 0, and 1. So there's no more augmenting passes, so we do the summation, 2, 3, 4, 5, 6, 7, and the flow would be equal to 7. So we have the solution here, so you can recheck it if you want. As a last exercise, so we have also to calculate the maximum flow from S to T, so you can also check if you can find a minimum cut at the same time. So we'll keep that for you. So use the Fulkerson to obtain the maximum flow again, so we need to find an augmenting path. So the graph is already the residual graph. So SACT, I can send 10, 0, 10, 0, 22, 5, 10. Another one, SBDT, 15, 10, 15, so it's 10, 5, 10, 20, 5, 10. Do we have more augmenting passes? So let's check. So on this way it's equal to 0. On this way I have 5. 5. So if I want to send from B to D is equal to 0. From B to A I can send 5, not 10. But from A to C I have 0. So there's no way, if I'm reaching A, there's no way to go to T, and if I'm reaching B, there's no way to reach T. So this is the maximum flow, and it's equal to 20. So in some, as I have started the chapter here, so the network, we are considering just two terminal networks. So but what if, for example, I had this network, so I have AB but I don't have S. So obviously you can add a super S and then link it to A and B. So it's very easy to do that. So even if you have multiple sources, you can create a super source and then link it to that. So you can add here zeros in order to just, so obviously you cannot add 0 because the flow would be equal to 0. So you can place infinite and then calculate the maximum flow. So as a last part is about the network and matching. So let's suppose that we say that network flows can be used easily to solve bipartite matching. So let's suppose I have those two sets and I need to find a matching. So as I have said, I can add a super source and I can add a super sink. So let's suppose I want to achieve a maximum. So we create a network from the graph. So we introduce two new vertices S and T. So we put arcs from S to each vertex in the first set A, and we direct all edges obviously from A to B, and put in arcs for each vertex in B towards T. Next, the capacities would be all equal to 1, and then we apply our algorithm. And when the maximum flow is found, this saturated arc obviously from A to B correspond to a maximum matching. So this is the algorithm. So given a bipartite graph with part A and B, we suppose we want to achieve maximum. So we direct all edges, we create a network, we add two vertices S and T, we put arcs from S to A and from all the vertices of B to T. The capacity is equal to 1. We apply the algorithm, and then the saturated arcs would be equal to the matching. So there are parts that are not covered in this chapter, which are the Manger theorems application. So we can use maximum flow theory to verify Manger theorems in terms of cut vertices and stuff, but we will not be covering that because this is not the scope of our course. So we'll be moving to model in order to implement the Fulkerson algorithm. So we need to implement Edmonds Karp algorithm. So we have to write our function in source. So we have the predefined values here. So the vector of integer, we have the maximum v, so it could be maximum equal to 40. Okay, we have the infinite value. We have the adjacency matrix or the residual graph. So we call the residual graph. So we have a 40 by 40 matrix. We have the value of the maximum flow. We have F, S, and T. So S is the source, T is the sink, and F is the minimum flow that we can find on an augmenting path. We have a vertex of P. So this is just to record the BFS. Obviously, we'll be using a Q. So this is the reading of the graph. So we are reading an adjacency matrix using weights. So we have here the vertex and the weight, and we are placing it into the adjacency matrix. So obviously we'll be writing the solving function. So we'll be using BFS. We want to find the spanning tree using BFS. So we'll be looping over the Q, we'll be dequeuing. We'll see how we will do that. So we'll be calculating distances, obviously, because we need that in order to loop over the adjacency list and to find the augmenting path. So let's start. So we have here int sol, and it will return the maximum flow. So we have, at first we initialize the maximum flow to 0, and I'll be looping infinitely because, as we have told you, whenever we are using BFS, there are at most v multiple e augmenting passes. So we'll be looping infinitely, and whenever we have reached t, we will be ending our search. So if I cannot send any more flow, so if I'm trying to find an augmenting path and the flow remains 0, so there's nothing I can send, so I will end my loop. So this is what we have F. So f is the value of the flow, of the current flow, the augmenting path. So at first is equal to 0, and as long I can find f greater than 0, I will add it to, so I will write it here. So if f is equal to 0, I will do a break. So if I'm doing all the stuff here and at the end I can no more send flow, so I will terminate my program, and obviously if it's not equal to 0, I will be adding it to my flow. So what I will do that here, I will run BFS. So we run BFS. So for that I will be using a distance. So distance, it's a vertex of distance. So it will contain, so if our maximum is equal to 40, so let's say max v. So at first I will initialize it to infinite. So infinite here, as we have, so we have used the constant. So this is my first one, and distance of the source, it would be equal to 0. Obviously I will be using a q because I'm doing a BFS, so we call it q, and I'll be pushing the first vertex, which is s. Then so we have also here p, so it's the parent. So this is for the spanning tree. So p dot assign for s. So at first I need to do that to initialize it. Obviously it's equal to -1, and the parent. So let's write here. So it will record the spanning tree. Record the spanning tree from S to T. So this is the passes that I need to find. So this is just initialization. So next I will do the BFS. So as long as the queue is not empty, queue dot empty, I will try to pop one of the front element and then pop it. So int u equal q dot front, then q dot pop. So I have the front element, and then so if u is equal to the sync, it means that I have find my spanning path or spanning tree. So I have found a path from S to T, so there's no need to continue my BFS because I have found it. So break. So I will get out of we stop BFS when we reach sync. So if I didn't find that, I need to loop over the adjacency list, so the set of vertices. So int v equal, okay, int v equal to 0, v less than the max v. So I'm looping here using the adjacency matrix. So we have rarely done that. V plus plus. So if there's no, so if the residual graph is equal to infinite, because you have initialized it to infinite, it means there's no an edge between those two. So if the residual graph of uv is greater than 0, so it means if there's an arc between u and v and the distance is equal to infinite, it means we didn't reach it yet, and the distance of v is equal infinite. So the distance of v, so this is the same as Dijkstra, equal distance of u plus 1. But we are using here just the BFS, but it's a bit modified. Q dot push v, and then the parent of v is equal to u. So this is our BFS. So let me repeat. So we have looped infinitely. So this is due to Edmonds Karp. So we are looping as long as, so we'll be calculating here an augmenting path. So if the flow on this augmenting path is different than 0, it means that, okay, there's a potential that I can find another augmenting passes. So I will not end, I will continue. So I will add this flow to the maximum flow and then repeat. If I found a path and the flow is equal to 0, it means there's no more augmenting passes. So I will end. So in my way, I will be doing BFS because this is the idea of Edmonds Karp. So I'm using a Q. I will be looping over a queue, so I'm just here trying to find a path. So, and we are using it, so we need to find the maximum path, so this is why we are using the distance. So while I'm looping over the queue, so level by level, if I reach the sink, so I will end. Otherwise, I will be looping over the adjacency matrix and see which one I can take. So I'll be looping constantly. So for each of the vertices, if there's in the residual graph is greater than 0, so if there's an edge, and the distance is equal to infinite, it means I didn't reach it yet. So I will update the distance, so just equal +1, it means that it's just on the next level. I will push it, and I will say whose is parents. Then, obviously here, I need to find the augmenting path. So I will write a function, so augment. I will try to augment a t. So we will find the minimum edge weight f along this path, if any. So t, and we'll start from infinite. So t in our case is just the value of the sink. So I'm just trying to augmenting the value, so augment here till the vertex which is t. So I will write it here. So find the minimum edge weight, which is f here, because I will be using f, so as if the return value is f, but it will be used directly. So f here along the path. So this path, not any path, because I've already found this path. So I have p here, this path, if any. So I have calculated a path here, which is in p, and then I need to check the minimum value on f. So we'll write the augmenting path. So void augment. I have here int v, so this is the sink, and int minimum edge. So we need to find if there's a minimum edge. So if the vertex v is equal to s is equal to source, so obviously it means that I'm still starting from, so I'm starting from the s. So the f would be equal to the minimum edge, so it will be infinite, because obviously I didn't find the source, and I will return. So we are doing here a traversal from s to t. So record minimum edge in a global variable f. So f it's already a global variable, okay? So there's no need to do a return or stuff, it's already in f. So else if the parent of v, so here v, if the parent of v is equal to -1, it's different. So if it's equal to -1, it means it's not part of the spanning tree. So it's different than -1. So I will go back. So I will do a recursive call. So I will do augment the parent of v, and I will take here the minimum between the minimum edge and the residual graph of p of vv. So this is a bit recursive, this is not that easy. So this is a recursive function. So my stopping condition is whenever I'm going back because this is the BFS traversal from S to T, but I'm doing it recursively. So I'm starting from T and trying to reach S. So if I reach S, and I'm calculating here the minimum value. So I'm starting from infinite and I'm trying to finding the minimum. So obviously F would be equal to minimum. If while looping, I have the parent of v is different than -1, because the recursive call would be on the first parameter. So if it's part of the spanning tree, I will do it recursively. I'm going back recursively. So it's the so p of v. So it's the augmenting path of p of v, as I'm starting from p of v, and it's equal to the minimum of the value that we will be calculating and the residual graph of p of v. Whenever I'm doing that, whenever I'm going back in the unwinding part, I will be updating the residual graph of P of V V and the residual graph of V P of VV. So this is the residual graph. Whenever we are doing the augmenting path on the way back, so this is on the way back. No, this is on the way going forward because I'm going from P to P of V. I will decrement the flow, and on the way back, it means P of VP of V. I will be incrementing the path, the flow. This is quite difficult in terms of implementation. So I will repeat. So this is my augmenting function. This is very important. So this is a stopping condition. So it means that if the vertex is equal to the source, whenever I'm going back, so the flow would be equal to the minimum edge. So because we have finished, because we have found the minimum edge. Otherwise, I'll be recursively going back. So I will be calling the parent of V. So at first we are calling T, then parent of T, then the parent of T. At each time, it would be equal to the minimum of the minimum edge. So at first it's equal to infinite, and the value of the ongoing edge. So it's P of V, V. So from the parent to the V. And on the way forward, I will decrement the flow whenever I'm going back after the calling of the function. And on the way back, from V to the parent of V, I will be incrementing the flow. So if you have understood the algorithm, it's very easy to check here. So let's check and see if it's correct. So we have some mistakes. Let's see. So we have V++, V less than V max. Left operators, semicolon. Insole. So we didn't return the flow. So return MF. So it's correct. So let me repeat quickly. So the augmenting function, so its purpose is to find the minimum edge on this spanning tree. So we have calculated the spanning tree. So we have the parent of each vertex. We have worked backward. So we have started from the sink, and we needed to find the minimum to the path till the source. So we have at each time the parent of each vertex. So the vertex, if I have reached the source, I will return the minimum edge. Otherwise, I will recursively try to go backward. So it's the augmenting path of the parent of V and the minimum between the minimum edge and the forward edge. And whenever I have found, at the same time, I'm updating the forward edge and backward edge. And here we have just a modified version of BFS. So we have rarely used BFS, but this is the correct implementation of Edmonds. So this is the implementation, and this is the last algorithm and implementation and part of this course. So if you have any questions, do not hesitate to use the forum, obviously, and to write to me, and obviously I will write you back. And happy ending for this course.